All right. So it's a pleasure to welcome our speaker today. It's Jordan Watts from the University of Colorado at Boulder. So as you may remember, he was actually a postdoc here not such a long time ago. And today he is going to tell us something about colimits as limits and limits as colimits with applications.
Great. Thank you very much. It's great to be back. It's the first time I've been back to Illinois, ignoring O'Hare, since I left, actually, a couple years ago. So I'm not actually going to rigorously define any words in here, but I'll give you pictures. So let's start with colimits. So fix a category C. And for me, what a colimit is, you can imagine a whole bunch of objects. I'm very visual, so I just draw these as pictures. So you have a whole bunch of objects sitting inside your category. And maybe you have a bunch of arrows going between them. And what you want is something over here, some object of your category. In fact, I'll use colored chalk for this. Some object of your category with a whole bunch of arrows going like this, such that, well, if you have anything else that looks like this, maybe another object with a whole bunch of arrows such that everything commutes and so on, there's going to be a unique map going this way. So I like to think of it as supremums in the real numbers. You think of these as a bunch of real numbers, and then there's going to be some supremum of them or something like that, except instead of real numbers, we have diagrams. So this is one way to think of colimits. So let's just do a simple example to illustrate exactly what this is. So let X and Y be topological spaces. And I'll have two maps from X to Y, F and G are continuous. And that's a diagram. There's two objects, two arrows. What is the colimit of this thing? Well, what you can do is form this equivalence relation on Y generated by the following thing. So I'll ask y1 to be equivalent to y2 if there exists an x in x such that f of x is equal to y1 and g of x is equal to y2. Now, for those of you who are very, very careful, you'll see this is not an equivalence relation, but you just generate an equivalence relation from this. You throw in reflexivity and so on. So this is called the coequalizer, but for me it's a quotient. What's important here is that this is a quotient. Great. Now I tend to do more differential geometry, differential topology stuff, so I want to port this idea over to the smooth categories. So I'm just going to essentially do the same thing. Let G1 to G0 be a Lie groupoid. So let me just very briefly remind you what that is. It's, well, it's a category. In which G0, G1 are smooth manifolds. All the usual structure maps having to do with a category are smooth. So the unit maps, sending an arrow to its domain, to its codomain, these are all smooth. Composition is smooth. All structure maps are smooth. But to make sure we stay in manifold world, we need to ensure that source and target the domain map and codomain map. These are surjective submersions. It's a rather long thing to put in brackets, but there it is. So this is the source and this is the target. Okay, so I'll actually do some more concrete examples of this, but let's just start with the groupoid. And what I typically like to do is look at its coequalizer. So its notation is usually like this. And there's only one thing that this could be, but as some of you might know this, there's a glaring issue here. That's not a manifold. So what do? I need to do something about that. So I'm going to leave us here for a minute. This is not a manifold. At first I thought someone was choking, and then I realized, oh right, there's a baby in the audience. I was thinking, it's not that bad yet, is it? So I just want to quickly define limits. And I mean, in fact, I could really define it over here. I will define it over here just to be efficient. So a limit, it's essentially the same definition. You start with a category. I'll erase all the purple stuff. You have a collection of objects, maybe a bunch of arrows in between them, and then you look for some object over here with a bunch of arrows going in. And these are all maps, and everything's commutative as it should be. And then you also ask for the universal property. So if there's some other object with, again, a bunch of arrows going everywhere, then there has to be a unique map here. That's the way it is. Example, again, I can have this setup. And I can look at what's called the equalizer, which is the limit of this diagram. So here I'll define z to be all x and x, such that f of x is equal to g of x. So let's make it, let's get a smooth example of this. And I like to take x to be rk, y just to be r. I'll take this map to be a polynomial, this map to just be the zero map, and then my z, well, it's all x in rk, such that p of x is 0. It's just a variety. Maybe singular, but a variety nonetheless. And again, you can ask, well, it's not necessarily a manifold. What type of structure are we going to put on this? We want to talk about calculus on this. And I'm sure lots of algebraic geometers have answers for this, but I want to put a very specific type of smooth structure on that, as well as that quotient I just erased. So let me introduce a category so then I can stop being so hand-wavy. I'll write a warning first. We want some type of smooth category. Where we can talk about these quotients. And subspaces, or if you want, limits and colimits. So let me define that for you. So I start with a set x. Let x be a set. Some authors like to append the word Sikorsky here, but I just call it a differential structure. So a differential structure on X is a family of maps. We'll just call it fancy F. And I should tell you what type of maps. In fact, they're real valued functions. So let me, family of real valued functions. Satisfying two conditions. So first of all, well, we need to get differential in there somehow. So how do we do that? Well, for any smooth map in the usual sense between Rk and R, for any k, in fact, and for any k-tuple of maps from fancy F, we have that the composition is contained in fancy F. So that's where smoothness comes from. Moreover, this tells you that you have a ring. You know, it has addition and all of that. So that's the first condition we want. And the second is we want some type of locality, some type of sheaf condition. So with respect to the initial topology induced by F, this is the weakest topology such that these are all continuous. It's the one you would care about. So with respect to that topology, for every point there exists an open neighborhood, U. Sorry, let me insert something. I need to start with a function. If I start with a real valued function such that about every point there exists an open neighborhood and a function in fancy F, such that the restrictions to U are the same, then F is in there. F is in fancy F. In other words, if I have a real valued function that locally looks like it's coming from fancy F, then it must globally be in fancy F. That's a typical sheaf condition that we want. So that's it. That is a differential structure. And X equipped with one of these is called a differential space. This is a differential space. And I can say a function from xf to yg is smooth if the pullback of g is in f for all g. So that's what you would expect, that pullbacks are brought into here. So this is a category. And it turns out this generalizes manifolds. It has varieties. It has your quotient spaces from proper group actions. It has everything you would care about. So in other words, all these limits and colimits are contained in this category. You can now do analysis on them. I don't know if that makes you happy or not. So let me give you a very nice example where I can use this and start pushing this philosophy that's in my title, colimits as limits or vice versa. But I just needed this category to even begin discussing things. So fix a Lie group, G, and a smooth manifold M. And assume we have an action. Then I want to go back to Lie groupoids very briefly. We have a Lie groupoid. It's the action groupoid It's usually denoted like this. I think I always get that thing mixed up, but I believe if you think of this as a creature with two arms that's doing the action, that's the direction it's supposed to be going. So this is a Lie groupoid where the objects they're points of M itself, and the arrows are G cross M. So it's enough for me to tell you what the source and target map are. So the domain of this arrow, which is a very general way of looking at it, is just M itself. It's just the projection onto the manifold. And the target map is the action map. So this is the standard groupoid you build out of an action. Great. So now I'm just going to assume my action's proper just for technical reasons. So if you're not familiar with actions, I have the following map. The pair source target, this has to be proper in the usual sense, usual topological sense. In particular, all the stabilizers are compact. So assuming this, well, what do we get? Well, we have a slice theorem. So I'm sort of assuming you've all seen a little bit of group actions before, a little bit of this differential topology. But if not, I mean, here's a crash course in it. So we have a slice theorem. For any x in M, there exists a G invariant neighborhood U and a G equivariant EQBT diffeomorphism, let's just call it F, from U to the following set. In fact, just really push that this is a quotient. This is modulo H, just so we don't have the extra notation that I have to define, where V, or maybe H, is the stabilizer of X, and V is the normal space to the orbit at X. So it turns out H actually acts on this. If you have a group action, H is the stabilizer of X, so it fixes X, but it'll act all around it, and then using linear approximations, you can imagine it acting on the normal space to the orbit. So this is the slice theorem. And what we get is that a neighborhood of the equivalence class of X is given by V mod H. So here I'm taking the following equivalence class. So remember, I had written this down before. This is my groupoid. But now my groupoid is just this action groupoid. So this is G cross M. Here's my source and target map. I get this co-equalizer. That's just my orbit space. And I can talk about where an X sitting here goes to down here. So I now can talk about the topology in terms of these local models around my points, which are just linear actions modded out by compact groups. So that's a quotient. I'm interested in the fact that this is a quotient. What type of smooth structure does this get? It's the functions on here that lift to H invariant smooth guys upstairs. This is the standard thing. So the smooth structure on V mod H consists of functions who lift to smooth invariant functions upstairs. Wonderful. What's amazing, though, is that combining these theorems of Hilbert and Schwartz, you get that there exists some giant n, well, maybe not giant, but there's some n, so that V mod H actually sits inside R to the n. This is a thing that you might do in dynamics or something like this if you're working on one of these singular spaces and you needed to actually get your hands dirty, work with vector fields, you might work with this. Great. So it's not just any subset, it's in fact a semi-algebraic variety. Exactly. So it turns out, and this is where Schwartz came in, this sits inside here as a closed subset, so you can just restrict. You don't have to worry about those sheafy things that locally are restrictions, but yeah. So here, the smooth structure. Are the restrictions. But these match the functions over here, the quotient functions. So I originally was viewing this as a quotient where the functions came from this whole structure. Now I'm viewing this as a semi-algebraic variety where the functions are coming from here, and it turns out I haven't changed anything. So now let me give you a very explicit example of what could possibly happen in this type of situation. So let's say I have ON acting on Rn. So just by rotations and reflections, very simple example. Anyone tell me what the orbit space of Rn mod On is? Think of the circle acting on a plane, or Z2. It's just a closed ray. So it almost seems like all of this stuff I've just been talking about is stupid because I can't even tell what n I started with. They're all the same. They're all this manifold with boundary, the closed half ray. However you call that. It's the closed ray, I guess. So who cares? Well, and here's where things start to become interesting. So I proved this 2 years ago, 3 years ago, something like that. And it's that if we start with an orbifold. So you know what? Maybe I should define orbifold first. Start with let G be a Lie group. Acting on a manifold M properly and locally freely. Locally freely is a fancy way of saying all of the stabilizers are finite. They're not just compact, they're finite. Then we call M mod G, the orbit space, an orbifold. That's not the usual definition of an orbifold whatsoever, but turns out it is an equivalent one. It takes a lot of work to prove that, but then M mod G is an orbifold. All it means is that locally, it looks like you're modding out by something finite. You need the Slice theorem to realize that, but that's what this is. So I was trying to think of a quick way of defining orbifold for this talk, and I thought, oh, I can just do this. Because otherwise, you need to get into charts and all these other things. So theorem is that if M mod G is an orbifold, then the differential structure on it sees all of the information that it needs so that you can actually rebuild the orbifold. You can rebuild the groupoid, the whole action. Contains enough invariance. Let's actually make this professional sounding. So it contains enough invariance such that the action groupoid can be reconstructed. And I'm not going to get into this, but for those of you who are familiar with groupoids, this is up to Morita equivalence, of course. Which is fine, because orbifolds are only defined up to Morita equivalence anyway. Why is this an interesting theorem? Well, because of the Schwartz result, our M mod G locally is a semi-algebraic variety. It's just locally subsets of Rn that are glued together in some way. And somehow the functions on there, if you play around with them enough, you'll actually be able to rebuild this space as a quotient. And I don't, even though this theorem is mine, I still don't really understand why. What makes those semi-algebraic varieties coming from orbifolds so special? Because as you can see from this example, it's not true for all group actions. If I know that this came from an orbifold, I will know it came from, well, when n is equal to 1. But in general, this space can come from other things. So that's the point of this. Somehow functions, even though they're a very weak structure, they treat it as though it's a semi-algebraic variety. It has enough to see what orbifolds. It has enough to sort of rebuild an orbifold from the orbit space. So who cares? Great. This is sort of an interesting example.
So could you give us an example which would be covered by this theorem, which is, as opposed to that example, which is not?
Sure. So you want just a different example?
No, an example to which this theorem applies as opposed to an example to which it doesn't.
Sure. Let's take, well, write it as R2. So Zn, Z mod n, acts by rotation. And this just gets you a cone like this. In fact, this is sort of the most interesting part of the proof of this result.
Okay. I see. But,
the functions tell you how pointy this is, and the pointiness depends on your n.
Yeah, okay, but I wanted like a Lie group which is not.
Oh, you want?
Yes, this is an example. But,
You want an example that wasn't an orbifold?
No. I wanted a group G, which is like a real Lie group. I mean, he gave me positive five.
You don't want a finite group? I can do that. So you want like a connected Lie group that you can take a Lie algebra of, something with content. Okay. Fine. So let's take S3 mod S1. So how does this act? This will be, well, I'm going to stuff S3 into C2, and I'll describe it that way. Let's see. So I have S1 acting on C2. And I'll define this action to be, say, e to the I theta A1, Z1, e to the I theta A2, Z2, where the GCD of A1, A2 is 1. And you can check S3 is an invariant subset. So it's an invariant submanifold. And if you mod out by S3, you're going to get one of these weighted projective spaces. So for those of you who don't know what that is, imagine a sphere. In this case, it's a sphere, two-sphere, where that is the worst two-sphere I've ever drawn. Here we go. Where this will be a point like this, actually, matching A1, and this matching A2. I'm completely ignoring the 2 pi's, 2 pi i's, or whatever else I'm missing up there, but yeah. This is an orbifold. The functions can tell you what the A1 and A2 are. And in fact, it's a project. It was a summer REU project with some undergrads and a graduate student to just look at circle actions. If you know that you have a circle action, can the functions tell them apart, essentially? And if there's no codimension 1 strata, then the answer is yes. Now, what else can you do with this point of view, this philosophy of, OK, locally I'm going to treat these quotients as subsets and see what that does for me? Well, it allowed me to do the following. So check my time. Well, let me just ask, symplectic geometry. Who knows what a symplectic manifold is? The talk is designed so that I define it. So I might as well just define it. So let me start with the definition. A symplectic manifold, M omega, is a, well, manifold, M equipped with a closed, non-degenerate two-form omega. Period. That's a symplectic. The omega is the symplectic form, and there we go. A group action on my symplectic manifold itself is symplectic. It's supposed to be my rounded arrow. If the action preserves the symplectic form. Now, for those of you who know a little bit of differential topology, you know that this is going to imply that the Lie derivative of omega with respect to psi is 0, where psi is a vector field induced by the action. So it comes from an element of the Lie algebra. And in fact, at this point, I'm really starting to push towards circle actions. So you can, there's like no ambiguity at all of where this is coming from. So here on after, G is just S1. That's not where the fun differential geometry ends. I mean, we all know Cartan's magic formula, or some of us should. We know that this is just d of omega with psi inserted in plus psi inserted in d omega. It's one of these infinitesimal homotopy operators. But omega is closed, and so this term just isn't there. And so we get that 0 is equal to this, which is another way of saying that psi hook omega is closed. Great. So I really want a Hamiltonian action. The action is Hamiltonian if further this thing is exact. So I have, there exists some function phi, smooth, such that, I mean, I guess for the purposes of this talk, I really don't need a minus sign. It's just there for convention purposes. So I'll get rid of it. There we go. Here, phi is called a momentum map. Or moment map, if you want. So for those of you who are familiar with mechanics and so on, think total energy of a physical system. That's what phi would be, or perhaps angular momentum. Symplectic geometry is very much motivated by modeling these classical mechanical systems in a geometric way. All right. What I want to do is take the symplectic quotient. So fix a value A in the image of phi. The symplectic quotient, or symplectic reduced space, of M at A, or whatever word you want to throw in there, is it's usually denoted with 2 bars. Again, I'm sticking to S1 for now. And it's defined to be the pre-image of A modulo S1. So it turns out this momentum map, its level sets are invariant. That will just follow from the definition and so on. And so I can mod out by S1. Now, if A is a regular value, then it's not hard to show that this is an orbifold. Basically, this equation is going to tell you that A is regular if and only if G, or in this case S1, is acting locally freely on this level set. Of course, if A is regular, this is a manifold, and then so this would be an orbifold. If A is not regular, it's critical, then all of a sudden things are interesting. And there's a question: what is the symplectic quotient? Now, Shamar and Lerman, back in '91, gave a very good answer. They said, well, this is a stratified space. It has a Poisson structure such that all the strata become symplectic manifolds on their own, and they're all glued together in a nice way. But you can still ask questions about this. This is not the end of the story. So I'm going to make this question a little more specific in the following way. So let me just fix A critical. A critical value, A critical value. It is a result of Schwartz, Herbig, and Seaton. So Schwartz, which is not alphabetical at all, but oh well. That in the case of a critical value, this is an orbifold if, and only if, the dimension of it is less than or equal to 2. Here again, A is critical. So obviously, if it's a regular value, you get an orbifold. But it's going to be an orbifold only if this is true. So what about the others? Can you say anything about that? So my question is going to be, does there exist a group, Lie group K, and a manifold N such that K acts on N got my headers mixed up, and N mod K is going to be diffeomorphic to this thing. That's the question. So is this diffeomorphic to the orbit space of a Lie group action? And it turns out the answer is no, unless it's an orbifold. And because of Schwartz, Herbig-Seaton, we know exactly when it is an orbifold. So no. I love just one-word theorems, no, but in this case I do have to actually add something. So unless this is an orbifold. And so I can append this theorem to the Schwarz-Herbig-Seaton theorem and say it only happens if A is regular or if the dimension of the stratified space is less than or equal to 2. Dimension being defined generically. You find the biggest stratum.
And of course here you're not insisting that group K have finite stabilizers, right?
No, you know, I will. I should. Does there exist a group?
Group has finite stabilizers.
No, I'm sorry. Proper. I want the compact stabilizers. But no, obviously, yeah, there exists a group K such that this is proper. Thank you. I do need that. I do need that.
Yeah, I believe that.
So let me actually give an idea of the proof, because it jumps around math a tiny, tiny bit. At least for me, it taught me.
That's another question. So
Yeah.
are you proving that?
So for those of you familiar with groupoids, note I could not phrase this question in terms of groupoids, because this is a symplectic quotient. There's no groupoid living above it. My level set phi inverse of A is not a manifold. So there's no way to express this in terms of groupoids. That's why I like this language. I can talk about diffeomorphism directly on my orbit space.
And this is the differential structure coming from the invariant functions.
Exactly, yeah. So idea of proof, spell. It goes like this. So first of all, it's enough to prove stuff locally. And if I can prove stuff locally, I just go to linear models. So local linear models. So in this case, this is an S1 action. I'm going to get, so if A is critical, what I'm going to get is this cone for phi inverse of A. It's a cone over the following space, where this space is some, technically they're ellipsoids. It's an ellipsoid cross another ellipsoid, but I only care what it is up to diffeomorphism at this point. So you take that space and you just form a cone. Now if I mod it by S1, I have my symplectic quotient. And here I get, again, some type of cone. Maybe it's going to have that pointiness like the orbifolds. Great. That's locally what my space will look like in general. Now, we know from stupid things coming from Lie group actions, the fact that we can always find a higher metric and treat everything as if it's an orthogonal action, that n mod k locally about the same point, it's also going to be a cone, except now this space is going to be some sphere modulo some subgroup of k, some stabilizer. It could be k itself, but it's going to be some group. And so the question is, can I ever find a group L? Maybe I shouldn't use L here. Maybe I should use P. I'll just use P. Can I find a P and an L such that that space is going to be diffeomorphic to this space? Now, the fun thing is that this is coming from a manifold. It's S1 modding out a manifold. And in fact, you can prove this is an orbifold. This on its own is an orbifold. You just check all the stabilizers. They're all finite. So that's an orbifold. So since Sn cross Sn modulo S1 is an orbifold, and we assume I should have said this in the beginning. We're assuming that we can actually build this n and k. And we are assuming that this space is diffeomorphic to SP modulo L. Then my theorem about orbifolds basically tell you the corresponding groupoids have to match, or at least up to Morita equivalence. So this thing. So let me just end with the following. So what do you do at this point? You look at their classifying spaces, their categories, you build their NURB, do geometric realization, a whole bunch of crazy abstract stuff that I don't know if has any meaning in the real world, but you do it anyway. It turns out that the geometric realizations, their classifying spaces, have to be weakly homotopy equivalent. And then you just look at a bunch of long exact sequence of homotopy groups, compare, and what you just get, it just falls out, is that the dimension of L has to be, the dimension of K has to be finite. It has to be 0. And so you come down to these cases exactly. And that's it. So, sorry, that was a bit rushed at the end. I think a lot of the interesting math is going on from here into the algebraic topology, but I'm out of time. So that's it.
All right. Are there any questions for Jordan?
So I have a question. So your result is stated for these quotients, symplectic quotients. You can ask, okay, what happens in general if I take the 0 level set of some function and divide out by, say, a circle? Right?
Okay.
And it seems like your theorem wouldn't go through, right? Because you wouldn't. I mean, I guess I'm asking, is there any natural generalization? I guess, look, I think what I just said won't go through, but maybe there's
right.
something in between.
Yeah, you would need, first of all, for the quotient to have this nice cone-like structure, stuff like that. You need to be able to build groupoids, which I guess you can, but you have to be a little bit careful. There's a lot of stuff in your level set you have to check. But at least for me, the next step is torus actions.
Yeah.
And I don't think it's hard. It's just I don't.
Well, they're not really
Yeah, like SO3 or SU2 would possibly be natural. Yeah.
I was thinking you're going all the way to the final thing that
Oh,
is not plausible, right?
no, maybe someday. Not today. But, yeah.
Okay, thank you very much again.
Thank you.